Remember when we were talking about graphs of functions and what it was about a set of ordered pairs on the graph that made it a function? What mattered was that the y values were associated with x values so that each x value got a unique y value. That means that it goes one way from the x value to the y value, and for it to be a function, there has to be an unambiguous rule of association to get the y value out from the x value. We saw that it didn't matter so much that they were distinct y values for the x values. It could happen for a function to have two y values go with the same x value. If we want to keep distinct y values going with x values, it's an extra property that the function has to satisfy. It is called a one-to-one function. The function's one-to-one if distinct x values, so x1 different from x2, give distinct y values, so f of x1 different from f of x2. Here's what you could do for the ordered pair version of that. If you look at a set of ordered pairs, you could check to see if distinct x values go to distinct y values, so are y values used over. 1 gets used with a 1, 2 with a 4, 3 with a 9, 4 with a 16. Never is it the case that there are extra y values, that there's a y value used more than once. And that's enough to say that this is an example of a function that's one-to-one. If you look at a set of ordered pairs, minus 2, 4, minus 1, 1, 0, 0, and 1, 1, you zero in on this. Notice that minus 1, x goes to 1, and 1 goes to 1. So both those x values, minus 1 and 1, have the same y value. That's enough to say that that's not a one-to-one function. It is a function, just not one-to-one. There was a geometric criterion you could use to decide if a given relation, a set of ordered pairs or a graph in the plane, was the graph of a function. It was the vertical line test. This condition is the horizontal line test for one-to-one functions. If a horizontal line intersects the graph in at most one point, the function's one-to-one. You could apply that. Here's an example of a function, f of x, 2x squared minus 5x plus 1. That's a parabola. If you graph it, and you can notice that lots of ways to draw horizontal lines that would cross the graph at two places. Here's one. It crosses it to the left of the y-axis and to the right of the y-axis. This is enough to say that it's not a one-to-one function. In terms of that definition, here are two x values, looks like about here, and a symmetrically placed point about here. Two x values that have the same function value. Same y goes with this x as went with this x. And that's enough to say that it's not a one-to-one function. Let's look at another example. How about x cubed plus x minus 2? This one is a cubic, and the graph of the cubic is a swoopy thing that starts at minus infinity, goes through 0 and up to plus infinity. This time, no matter how you try to draw in a horizontal line, you'll find that it crosses the graph at one point. It looks a little odd here just because this is going across with the resolution of the screen. You miss one of the extra point that's here, and so this one does, even though it looks like it might cross several points here, if you zoom in, it's a single point, and that's the definition isn't violated. Well, what's special about one-to-one functions is that you have a rule for going from an x value to a y value. If it is a one-to-one function, you can go unambiguously back from the y value to the x value. So instead of going from x to y, you go from y to x. You undo what the function did, and that happens for an inverse function. So an inverse function, start with f, and this f minus 1 is going to be the function that undoes what f did. So you start with x, and f of x goes to some y value. What's supposed to happen for the inverse function is it, applied to that y value, gets you back where you started, gets you back to the x. And f inverse of f of x equals x, f of f inverse of x equals x are the two backwards and forwards ways you could go to relate y to x, x to y, to relate the graph of a function to the graph of the inverse. Here is this sort of a generic set picture to say what's going on. If you think about the top part of this picture, a function from a domain, values that arise the range. Now if you turn it around and think about going backwards for a one-to-one function, you can go backwards from points in the range to recover the points in the domain they came from. That's what the inverse function does. F goes from y's to x's maybe. F goes from x's to y's. F inverse goes from y's back to x's. The domain of f is where f starts. The range of f is where f finishes. The domain of f inverse is where f inverse starts, so that's the set of y values. And the range of f inverse is where f inverse finishes, that's the x values back. So you can keep track of the relation that the domain of a function matches the range of the inverse function. And the range of a function matches the domain of the inverse function. A nice geometric way to recover one function graph from another, to recover the graph of the inverse function from the graph of the given function, is that the graph of the function and the graph of the inverse are symmetric, a mirror image in the diagonal line y equals x. The reason that works is reflecting a point about y equals x has the effect of interchanging the coordinates. It goes from x then y to y then x. Interchanging the coordinates reflects it about that point, and interchanging the coordinates is what the inverse function should do. It should go not from x to y, but from y to x. So it switches the role of the independent and the dependent variable. So this symmetry by switching the coordinates is a useful thing to calculate inverse functions algebraically. Here's a function, f of x is 5 over x minus 3, defined for x different from minus 3. And the function is one-to-one, so let's calculate what its inverse would be. It relates a y value to an x value this way. Y is 5 over x minus 3. Let's interchange the x and the y values to do the reflection about the line y equals x. Instead of y equals 5 over x minus 3, it would be x is 5 over y minus 3. Those two they're different functions, but you can take the version from doing this interchange of variables and recover y as a function of x from that. The approach would be to first cross multiply, so multiply both sides of this equation by y minus 3. It says xy minus 3x is 5 if you do that. And now solve this for y. To do that, I'm going to isolate the y terms on one side and every term that doesn't involve y on the other side, so I can add 3x to both sides to do that. And then I'll divide through by the coefficient of y, that is x. So y is 3x plus 5 all over x. And that's the inverse function that goes with the original function as it was given. If you graph this function and you graph the inverse function, you find that the graphs are mirror images about that diagonal line y equals x. So 5 over x minus 3 and 3x plus 5 over x are my pair of functions, a function and its inverse. Let's algebraically verify that they are inverses by checking that algebraic condition on what has to happen. We have to have f inverse of x to be x. So f composed with g of x, as it's given, would be, well, let's do it. G of x is 5 over x minus 3. So f of g of x is f of that expression, 5 over x minus 3. Well, f of x is a fraction with 3 times the argument on top plus 5 and the argument on the bottom. So let's do that. 3 times the argument, 5 over x minus 3 plus 5 on top, 5 over x minus 3 on the bottom. We can simplify that by finding a common denominator, multiplying top and bottom by x minus 3. And if we do that, let's see, now it'll cancel. I'll do that on the next slide. So let me recover this, and this will start off the next slide. So that's what we have, and let's multiply through top. The x minus 3 cancels, so it's 3 times 5 is 15, and 5 times x minus 3. And on the bottom, x minus 3 cancels, it's just 5 that comes out. Notice that you can combine like terms. 15 plus 5x minus 15 is 5x on top, 5 on the bottom, and that cancels to give plain old x back. It not only works for f of g of x, but it also works for g of f of x, g of 3x plus 5 over x, that's what f of x was, and then g applied to an argument. Remember, it was 5 over x minus 3, so the argument is on the bottom minus 3 with 5 on top. So let's put 5 on the top and the argument 3x plus 5 over x minus 3 on the bottom. Common denominator, let's clear out the fractions by multiplying top and bottom by x. 5x on top. X cancels when I multiply across on the bottom. 3x plus 5 over x times x is 3x plus 5 minus 3x. 3x minus 3x goes away. 5x over 5 is x back. So either f of g of x simplified back to x, g of f of x simplified back to x. So you start with a value, apply the function, apply the inverse, and you're back where you started. Start with a value x, apply the function, apply the inverse, and the x that you start with is the x that you end up with. You're back where you started. I think about inverse functions and these calculations as like playing cat's cradle. Did you ever play that game with string and you loop the string all around the fingers on your hand, and if you do it right, you can take one place and pull and all the knots fall away and the string just falls off your fingers. What's happening here is this is all tangled up algebraically, but you pull on it the right place, you simplify, and it all falls away, and you're back with just a plain old x. What you started with is what you end up with, and everything else falls away. Inverse functions. We're going to be doing a lot with these this semester, and we'll talk about inverse trig functions in some detail and review some of this stuff when we get to the inverse trig function stuff.